So thank you all for coming. I'm Sunny Wang from City University of Hong Kong, also the Physical Society of Hong Kong. I'm sorry that I couldn't speak Cantonese, but I hope I saw that many of the general public come to listen to my talk, so I replaced the English PPT by traditional Chinese. So the PPT is in Chinese, and then I will speak English, and feel free to ask questions. I'm also very honored to kick off this Science in the Public Service series. Actually, in the past 3 years, I have delivered more than 30 public talks, either in the high schools or in the public locations. So I think the interest from the general public, either high school students or general public on quantum science is very important. It indicates that this is something that people have curiosity on, and we welcome you or your children to come to CTU to study quantum physics. So let's start the journey to the exotic quantum world. Okay? So I'm Sunny Wang. I graduated from Peking University in Beijing, China. I got my PhD from Columbia University, and then I did a postdoc in the University of Maryland, United States. I actually came to Hong Kong exactly 10 years ago, starting as an assistant professor in CTU. And then I was promoted to associate professor about 5 years ago, and I served as associate head for a few years. So my research interest is theoretical physics, quantum physics, and condensed matter physics. Okay? So this is UNESCO. UNESCO is the United Nations Education, Science, and Culture Organization. So they have made a proposal, which is passed by the United Nations, to declare this year, 2025, as the International Year of Quantum Science and Technology. And why? Because exactly 100 years ago, just a few days ago, actually, is on 1925, July 29th, not about 2 weeks from now, right? So this German guy, Werner Heisenberg, he published a paper. Later, we call matrix mechanics. And then a few months later, another guy named Schrödinger, he published another paper we call wave mechanics. And this made the quantum physics that we know today, which actually completely changed our world. So the United Nations, UNESCO, held celebrations for this very significant event this year. So this is in Paris, in the UNESCO headquarters in February. And then this is the Assistant Director General, IYQ 2025. And then there are quite a few Nobel Prize laureates there. And this is Phillips, this is Wheeler. And then this is some representative from different countries. And I was sitting back there representing Hong Kong. Okay? So, right, so this is the magazine where Werner Heisenberg published his paper, Zeitschrift der Physik. So basically, you believe or not, almost, more than half of the modern technologies are based on quantum mechanics. If I tell you, hey, I give you money, let you travel back 500 years ago, and you become an emperor, would you do it? I wouldn't do it, because there's no YouTube, there's no video games, there's not even light, right? There's no LED, nothing, right? So we know that what has brought human being to the current way of living and way of working is Industrial Revolution. So the first Industrial Revolution is due to Newton, Watt, the invention of steam machines, right, which harness the mechanical and thermal property of matter. And then the second Industrial Revolution we know is about electricity. Edison invented this light bulb. And then there's Marconi invented the telegraph, and then Bell invented telephones. We used the electro and magnetic property of matter, and which ignited this Industrial Revolution the second time. The third Industrial Revolution, or the Information Revolution, we all know is based on semiconductors, but you may not know it, right? So the reason that we can harness semiconductors is because we understand quantum mechanics. Otherwise, right, many of the secondary school students, the periodic table. There's a group called carbon, silicon, germanium, tin, and lead. So they are all very similar chemically, but they are very different physically. Even carbon, you have diamond, you have this pencil, you have other charcoals. They look very different. diamond is very shiny, and the coal is very shabby, it's very dark. Why is that? It is only because we have understood quantum mechanics, in particular superposition, that we developed something called the band theory. And then we understood, these are insulators, and these are conductors, and we can actually make semiconductors. Actually, we can make different type of semiconductors, P-type, N-type, which leads to diodes and transistors. So we have transistors, we have lasers, we have the solar panels, we have X-rays, MRIs, and most importantly, the computer that you have. They are all based on our understanding of quantum mechanics. So it is the quantum mechanics which is the backbone of the third industrial revolution, which is your life today, the internet, iPad, YouTube, whatever. And you might also have heard from the news that people are working on this, quantum communication, quantum computation, quantum cryptography, quantum sensing, quantum imaging, right? We say it is either the fourth industrial revolution or the second quantum revolution, right? We human beings, we are on the verge of this technological revolution that we want to harness the higher level quantum mechanics, which we call the entanglement, in order to make useful things for human beings. Right? So these are also all based on quantum mechanics. And not only quantum mechanics have a lot of technological applications, it also completely changed our mind, changed our concept, our view of the world. This is basically why many of the general public, they're very interested in quantum mechanics. I've been in Shenzhen delivering this talk to a general public. They want to know, what are we? Where do we come from? What is the nature? What is the reality? Is it really there? Is this really red? Is it red always, whether I look at it or not? Or it is only red when I look at it. And when I turn my eye away from it, it is no longer red, right? I'm not asking a stupid question, you will know. This question has been in dispute between Einstein and Bohr since 100 years ago, since 1927. And if you have seen the news, only 5 days ago, I think either 5 days ago or a week ago, there was a meeting of Nobel laureates. And two of them, one called Zeilinger, Anton Zeilinger, and the other Alan Aspect, they argue about this again. So these are very deep questions that we are not able to answer very well, but we have some answer about it. So, if you want to know where we come from and what is the reality, and then you have to study quantum physics. Okay, so basically, quantum physics is supporting something like the stability of matter, and we will actually talk about it a bit later. You see the table here today. You also see the table here tomorrow. It will not vanish in one blink, and that's because of quantum mechanics. And there's also something very famous called the uncertainty principle. And many of the students may know it, that you cannot simultaneously accurately measure the location and the velocity of one object. Okay? And then there are also this wave-particle duality and probability wave, and most importantly, the measurement. Right? As I said, whether it is red because I measure it, or regardless of whether I measure it or not, it is red always. Right? So I've been given this talk many times in different countries. I also give this talk in the United States, in France, in Kazakhstan or so. And I try to find out some poets, some famous people from their country. Right? I find that in every country there's some very famous people, either a poet or an author, they try to say, the moon is very beautiful, right? So this guy, Su Shi, he said, when do we have the moon? You hold a cup of wine and you ask the heaven. But the question is that when is there? When is the moon there? Is it only there when you look at it? Or is there always? Right? As I said, 100 years ago, there was this very famous Soviet conference that Einstein and Bohr, they had different views. Bohr believed that the moon is only there when you look at it. And then when you don't look at it, it doesn't exist. And Einstein, on the other hand, believed that there's a reality which is independent of our measurement, that the moon is always there. So he feel very gloomy. He talked with his friends that I like to think the moon is there, even if I'm not looking at it. right? So this actually, it is this argument which ignited a pursuit of something called a hidden variable. And it is because we try to find out the hidden variable, we develop something called the Bell's inequality, and we find a Bell's theorem, which leads to the 2022 Nobel Prize in Physics, and which have actually changed our view of the world. I may not have time to talk about Bell's inequality today. I hope I might have a chance to tell you more about it in the future. Another thing is that something called a tunneling, right? So we have a classroom, we have a lecture theater, and there are walls. And if I run to the wall, you will say, this guy is silly, right? He will hit his head. I will hit my head and stop. But in the quantum world, you don't have to hit your head. You run toward the wall, and you can actually tunnel through. And this is something called a tunneling. And it's actually very important. It's happening every single second in your body, in my body. We know that the body, the life is based on something called the proteins. And the protein is a very large molecule which got folded, 1,000 times. And there are the signal transfer in the protein that if you wait until the signal transfer, it's going to be too long, right? But nature's telling you that, hey, you don't have to get over the wall, you get through it, right? So this actually makes the protein function very efficient. Right, so this is the wave-particle duality. We'll come back to this point a bit later. And now that I just show a figure, which is drawn by Hofstadter. So if you study condensed matter physics later, that you will know there's a very famous experiment called Hofstadter butterfly, very beautiful. So if you look at from far away, it says PARTICLE, right? Or if you look at it closer, it's WAVE. So wave and particle are actually the same thing, right? So here comes the godfather of quantum physics. There are two sentences. The first sentence, he said, everything we call real is made of things that cannot be regarded as real. So actually, there are two meanings. One meaning, I call it quantum 1.0. Quantum 1.0 refers to the period of 1900 to 1927 that we try to understand superposition, right? So when we try to understand superposition, we realize that all these particles are probabilistic. Right? Everything you believe is real, that you try to divide it, you reach the atom, you get out the electron, and you realize that it's all probabilistic. It's not deterministic. It is there, and it's sometimes not there, and you will not be able to know. You're only able to know the probability that in this space, how likely you can find the electron. So it is not the real that in your everyday feeling. This is quantum 1.0. Quantum 2.0, again, is based on entanglement. That, what you believe is real, but is it independent of your measurement? It is there, is it there, regardless of whether you look at it or not, or it is only there under your measurement. This is the argument between Bohr and Einstein and Zeilinger and Aspe. So the second sentence, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So I promise you that at some point in this lecture, I will stop and I ask you whether you feel shocked. And you will know that there's a good reason that I do that. Okay, so let's start our journey. What is exactly quantum mechanics? It is basically a branch of physics which describes the laws governing microscopic particles. But what are microscopic particles? You can say, well, it is atomic, atom, or even smaller. We know that things are made of atoms. Atoms are made of nucleus and electrons, and the nucleus are made of protons and neutrons are made of quarks, and quarks may be made of strings, right? So these are all fundamental particles. They're all quantum mechanical. And all this funny idea is not because we physicists, we want to make us look cute. Hey, you're intelligent, you're smart. No, it's not that we want to. We definitely do not want to accept all of these very strange concepts. I tell you stories later. But in the early 20th century, in about 1900, the development of technologies allowed human beings to see more than before. To see something that we were not able to see 100 years ago. We can measure the black body radiation, we can measure the atomic spectra, and then we try to explain those phenomena using the classical physics we have known for centuries, and we failed. And then we tried very hard, and we realized that the only way to understand all these new phenomena is to accept, we have to accept an entire new set of description of nature, and that becomes quantum physics. So there are many ways of learning quantum physics, and because we only have a 1.5 hour lecture, so let's start with an easy way, which is the quest of an atom. Right? We all know that we human beings, we make progresses because there are smart people who, after they had lunch, after dinner, they look at the sky and they ask questions. Right? So maybe if you are a secondary school student, you have a lot of homework. After you finish your homework, maybe it is time for you to sit down and look at this beautiful sky of Hong Kong and ask questions. Maybe you change the human being. Okay? So this question is 2,400 years old. What are matter made of, right? Can we infinitely divide matter? So this is basically a philosophical question. We all know that science doesn't appear up front. Science appears, actually science has a definite birth year, which is the year of 1543. Copernicus published his book on the motion of celestial bodies. And before that, there was no science, and all are philosophies. So in ancient China, about 300 BC, there was this philosopher Zhuangzi. He said that if you have a meter ruler, if a meter, and every day you cut it into half, and there's no end. You can continue this for infinite generations. So as he said, the matter is infinitely divisible. It is about the same time, maybe a little bit earlier, right? It's called Democritus. Democritus in the Greece, so he introduced this word. You can actually recognize this alpha is A, this tau is T, this omega is O, mu is M, so it's atomos. So atomos is the Greek for indivisible. Democritus, even without doing experiment, he believed that, we have such a beautiful world, that there are many different things. Some things are like this, something is hot, something is cold, something can move very easily, something cannot. And it is all because there's a fundamental unit which is making it up, right, which makes all of them different. It is what he called atomos. And today we call atom. He was correct, but unfortunately, what has been dominating people's head is not atomic theory, right? Why? Because there was no science. There was no experimental data which supports all these arguments. So in this Athens school, right, we all know this Athens school led by Aristotle and Plato, they believe that the world is made up by elements, right? If without science, if you haven't done any experiments, actually you realize that this is very, very convincing, right? So we are made up by fire, earth, water, and air. And then fire is both hot and dry, and the earth is dry and cold, and the water is both wet and cold, and the air is hot and wet. All seems very consistent, right? So that is why it is the element theory, not the atom theory, which has dominated people's head for more than 2,000 years. Right, so it is also, so there's a character which is missing. There's also atomic theory in the East we call Misius. Misius said, right, so if you have a body, right, and you divide the body up to the end, we call it that you reach something called the duan. So duan in Chinese, it means an end, right, a limit. I walk from 这一端 to 那一端. Or duan means origin, right? 你怎么无端端的生气啊? So the second sentence, actually, we are missing a character is this chopstick. So if you keep cutting the chopstick, and then you cannot do it further, and we say you are reaching something called the duan. So duan in Chinese means origin and the edge, which is something like the democratic atom. However, nobody believed him. Everybody believed that we have Tai Chi, and then Tai Chi gives you yin and yang gives you these 5 elements. The metal, the wood, the water, the fire, and the earth, right? So when I was a high school, college student, I sometimes play these video games, and this different kind of elements, they can kill, this water can kill fire, and the fire can kill earth, or so on and so forth. Right? So although the element theory is not correct, it's incorrect, it is the element theory but not the atomic theory which has dominated our head for more than 2,000 years until Dalton, until John Dalton, who is one of the fathers of chemistry. The other one being Lavoisier, whose story that we can tell a bit later. So he actually has a very good observation. You know, for those secondary school students, you must have learned the law of ideal gases. You know the Boyer law, you know the law of Gay-Lussac, right? So you know that for all these gases, be it chlorine, be it oxygen, be it hydrogen, you put the gas in a container, they all assume the same shape, regardless of different gases. Right? If you have put the gas in a container, you fix the volume, you close the lid, you fix the volume, and if you heat it up, and then what will increase? The pressure will increase. And then the amount of the pressure increase will be the same among all the gases. So it seems that all the gases are alike. Only one thing is different, which is called by Dalton, and that is how well it can be dissolved into water. We know that chlorine can be easily dissolved into water, and traditionally it has been used to sanitize the swimming pool. And I know that Hong Kong no longer uses chlorine. We use ozones, right? But in other parts of the country, in other parts of the world, they all use chlorines to sanitize the swimming pool water. So chlorine can dissolve into water very easily. Oxygen can dissolve a little bit for those fishes or so. And then hydrogen, very hard. So Dalton realized that how easy it is for all these gases to dissolve into water means that something fundamental is different between different gases. So he asked himself, why water cannot admit all similar gases in the same way? So this question I have carefully considered, and although I cannot entirely convince myself, I was almost convinced that the situation depends on the ultimate particle that made up these gases, the mass and weight of these ultimate particles. So I like to go back to the original literature. I'll also encourage my students to go to the original literature because one can learn a lot. But due to the time limit, we just don't go into a lot of details. There are actually, you can learn a lot from just one page. I can have a 2-hour lecture out of this. But just look at this. Number 1, which is a circle with a dot in the middle, which we call hydrog. What is it? Hydrogen. And number 3, carbon or charcoal. So number 3 is carbon. And you know that at that time, they still believe that carbon and charcoal are different things. Like, 100 years ago with Einstein, we believed that energy and masses are different things. And later on, we realized they're actually the same thing. And number 4 is oxygen. And actually number 2, azote. Don't worry, azote just means no life. Which part of the air which doesn't support life? Nitrogen, right? So he wrote this book, Elements, and there are actually a lot of stories on this page, but due to the time limit, let's go on. So Dalton's elements, Dalton believed that elements are made up by something called ultimate particles, and today we call atoms. So for the same element, the atoms that making them up, they are the same in sizes or in qualities or so. But for different elements, the atoms are different in sizes or so. And then the atoms are the ultimate particle. It cannot be divided, be created, and be destroyed. And the chemical reaction is just essentially the combination, separation, or rearrangement of these ultimate particles that what we call atoms. So from now on, the atomic theory are no longer philosophical thoughts. They become science. But as I told you, right, we human beings make progresses because we ask questions. Now it is very natural to ask another question, right? Can atom be further divided, right? So it doesn't take very long because now we have sciences, we have experiments. So this guy, Sir J.J. Thomson, who is a British physicist, he realized that when he heat the filament up in the dark, it will generate something very peculiar. It will generate some rays which bend in the magnetic field, what he called electrons. And he also realized that these electrons carry negative charges. So since the filament contains atoms, the electrons come out from atoms. It means that the atom have internal structure. There are electrons and there are other things, what we don't know yet. And he also measured, he shoot the electron beam into a magnetic field. And if you studied, high school physics, you know that the electron will draw a circle. And the circle is actually very, very clear, very easy to measure. And by measuring the radius of the circle, you can know the E or M, the charge divided by mass of the electrons. And just knowing E or M is not enough. And it is another American physicist, my alumni, Millikan, he did something called the oil drop experiment. There was some dispute, but he successfully gave to human being the E, the amount of the charge that electron carry. And now we know E over M. We know E. What do we know? We know the mass of the electrons. But after we know the mass of the electrons, everybody was shocked. Why? Okay, so I'm made up by atoms. I'm charge neutral. So when I shake hands with you, we don't electrify each other. I'm charge neutral, okay? So a charge neutral thing is separated into electron and other things. Let's say a hydrogen. It has one electron which has 1 unit of negative charge. And there are other things which must have 1 unit of positive charge, right? So that's why we can make the atom neutral, charge neutral. However, once we know the mass of the electrons, we realize that this part of the atom, which carry the entire negative charge, only constitute less than 0.1% of the masses. And the remainder, which carry the same amount of charge, is just positive, carry more than 99.9% of the atomic masses, right? So if you go to the secondary school physics book, it will tell you the mass of the proton is 1,836 times the mass of electron. Okay? So they carry the same charge, but one of them is very, very, very heavy. More than 99.9% of the atomic mass. And the other one, the electron, is very, very, very light, less than 0.1% of the mass of electron. And how does the atom look like, right? So J.J. Thomson put up the model, which called the plum pudding model, right? It's like a cake where all the positive charges, they distribute uniformly in the space of an atom, while the electrons are like grapes, like raisins, being scattered around. In every physics textbook, they will tell you that this model is wrong, and they will turn the page over. I'm sure that most of the teacher will tell you this model is wrong, and you will turn the page over. Okay, if you are a student who's interested in physics, I want to ask you this question, and why this is correct. In his age, at his time, given the experimental evidences that he had, why he made up this model. Okay, I leave these questions to the young friends. Anyway, today we know that this model is wrong because of this excellent experiment done by J.J. Thomson's student, Rutherford. So if this model is correct, if the positive charge is uniformly distributed in the space, then if you shoot some charged particle across the atom, it will feel more or less the same because all the positive charges are uniformly distributed all over the space, right? So above you and below you, you feel almost exactly the same repulsion or attraction. So if you shoot particles toward atom, more than 90% should just go right through. Even for those who who deflect from the trace, you only deflect a little bit because you are shooting over a cake. So here comes the Rutherford experiment. So he had this alpha particle source, and that's because he doesn't know what it is at that time. So people call it alpha, beta, gamma, X-ray. And today we know these are helium cores. Helium core, helium nucleus has 2 protons and 2 neutrons. So this is helium 2+, right? So we're shooting alpha particles, and then they are all focused into a very narrow beam. And this beam is shined on the gold, on a piece of gold, and it's going to scatter. As expected, more than 90% went right through, and then it just hit the screen on the back, no problem. What has been problematic is that about 7% is like being kicked back, 180 degrees, being kicked back to you. And you cannot understand if you accept the atoms are like cakes. You shoot a cake, and the cake kicked the bully back to you. Very strange. So that's why he wrote in his diary that it is the most incredible thing that he has ever seen in his life. It's like you are shooting a 15-inch shell on a tissue paper, but the tissue paper is like bounced the bullet back toward you, and you hit yourself. It's very strange. And it is for this reason that we have to accept a fact that the pudding model, the cake model is not correct. And we have to accept that there's a nucleus of the atom, that this one unit of positive charge, and this part constitutes more than 99.9% of the atomic mass, and they have to concentrate in a very, very narrow space, okay? So it is only this model can explain the experiment, that if you shoot an alpha particle toward the atom, most of the time you enter the empty space. So this particle just goes through. But 7% of the time, you're getting closer to the nucleus. And then the nucleus is much heavier and will just kick your alpha particle back. And that's the 7% of the backscattering that you have seen, right? We're problem solved, right? If you're a student, you do an examination, and there are 50 problems, and you solve problem one by one, right? There are 50 problems, and you solve one problem, there are 49 problems remaining. But I tell you, in scientific research, this is entirely different. If you're given 50 problems, you solve one problem, you don't have 49 problems. You have 500 problems. You solve one problem, it gives you even more problem. It is only when you entirely understand all of this, like you're going into a mystic forest. You go to Disneyland, you're going to a mystic forest. Whatever, the more you know, the more mysterious it is, the more foggy it is. It is only until you reach the end, you understand the entire thing, just in one blink, all the fog vanishes. Okay, so at this stage, it is just not just solving one problem, it creates another problem. And what problem it is? So we have a nucleus, and then we have electrons, and the electrons should circle around the nucleus, which there's no problem, right? However, at that time, we only have classical physics. And there's something called classical dynamics, and you don't have to understand the details, but you just have to trust me. That in classical dynamics, there's actually one German word. There are not many German words in physics. One German word called Bremsstrahlung. Bremsstrahlung means that radiation due to braking, right? You drive a car and you brake before you reach the red light. And then the Bremsstrahlung is telling you that if you have a charged particle, as long as it has acceleration, it will radiate electromagnetic wave, okay? So this fact is actually used today, when you have cell phones. Before iPhone, the cell phone looked very ugly. There's an antenna, there's an antenna. Now there's no more antenna, but antenna is still there. It's on the side of your frame. You can see from your phone that these particles are making this accelerated motion, harmonic motion, which generate electromagnetic wave, and then this wave reaches some base station. The base station take your signal and transfer underground to another base station, and then that base station produce a wave that shoots toward your receiver, right? So let me ask you a question, right? So if an electron is making a circular motion around the nucleus, does it have acceleration or not? Yes or no? Yes. Very good student. This is a place where it's very easy for students to make mistake, right? So circular motion have non-zero acceleration, even if the speed is uniform, right? Because we're changing the direction of the velocity, and there's something called the centripetal acceleration. Now, due to Bremsstrahlung, the electron circling around the nucleus has acceleration. And when it has acceleration, it will radiate energy. It will lose energy, right? If it loses energy, it will fall down from the space, and then it will make a spiral in, and then eventually it will hit the nucleus. Electrons have negative charges, and the nucleus have positive charges. When they meet each other, they kill each other. We call it annihilation, okay? It means that if this theory is true, all the atoms are not stable. If you are able to create an atom, it will disappear in 1 second, in 0.1 second. If you're able to see me, after 1 second, I'm gone. If you're able to make a table, after 1 second, it is gone. Is it the case in the real world? No. So that's why I say this nucleus model creates even more questions than it can answer. So here comes our godfather of quantum physics, Niels Bohr. In about 1920, about 1910 or so, he devised a theory that can more or less explain why the atoms like this. He said that you are not allowed to spiral in. All the problem is because there's a spiral, okay? You are not allowed to spiral. You can only stay in some fixed orbits. Number 1, number 2, or number 3. It's just like our human being. We live in the buildings. There are the first floor, second floor, or the third floor. You can take an elevator from the first floor to the third floor. You can take an elevator from the 5th floor to the 2nd floor. But you cannot jump from the 3.14 floor to 1.75 floor. There are no such floors. We don't allow such orbits in atoms, and this is called quantization. Okay, so Bohr said electrons are only allowed to stay in these quantized orbits in the atom, and you're only allowed to jump between these orbits. Okay? So by having this, he more or less explained many observations that we had, especially the hydrogen atoms. So these revolutionary ideas very soon become very, very popular. So electrons, they have to be like planets, right? So they stay in fixed orbits. You can call it Bohr model or planet model. So it is so famous that if I ask you, if I don't meet you here, I catch you on the street, I ask you, what is an atom? And you draw a picture, most likely you will draw something like this. And on the right-hand side, this is also a United Nations official agency who has been, watching this Iran nuclear program. This is called International Atomic Energy Agency. So you look at his logo, their logo, it is what? It is the Bohr model or the planet model. Again, answering one question won't reduce the number of questions that you have. It actually increases the number of questions. Why we are only allowed discrete orbits? It's very natural to ask this question. Actually, this question, it is very hard to answer, but since this is a popular science lecture, let me try to explain this way. Right? This is a very famous Japanese painting. There's this Fuji mountain far away in the back. There are also these wooden boats near the front. They are all made by particles. And then we also see the waves, right? So waves from this water. So particles are particles, waves are waves. But what if I tell you waves and particles are the same thing? So here comes the intelligence of this French guy, de Broglie. Okay, so actually there's a very interesting story. So de Broglie, he doesn't do a lot of work during his PhD, but he was inspired by Einstein's photoelectric effect. Photoelectric effect is that Einstein said that, okay, for light, if the light is shining on a surface, it behaves like a wave, but on the other hand, it can also behave like particles. And de Broglie said, okay, Einstein can say light are particles, waves are particles. Why can't I say particles are waves? It's fortunate that he's correct, right? So he said that although electrons are particles, but at the same time, we can regard electrons as waves. Actually, everything can have these wave properties. I can also have wave properties. It's just that my wave property is kind of small, that is very hard to measure. And once you accept that particles are waves, more or less you are getting closer to understanding the discrete orbits. And this is the famous old quantum theory by Sommerfeld, so one of the early quantum scientists. So the idea is that many of us played guitars or violins, the string instruments, And we know that string instruments can stably generate sounds because of this oscillation on the strings. And the oscillation is like fixed. It's not oscillation which is keep changing the pattern. It's like a fixed pattern. And this is what we call the standing wave. So there are basically two kinds of waves, two sets of waves. One going from left to the right, and the other one from right to the left. And the two waves, they interfere with each other. And when the size of this track, when the size of the string are good, they add up to each other, right? So they made up by standing waves. And that is also why you only have a few sounds for a fixed string length that can, that you can hear good sound, right? The lengths have to be integer multiplies the half wavelengths of these waves, right? So now we accept that electrons are waves. Waves have wavelengths. So the electrons should have wavelengths, right? So for the atoms to be stable, the electron wave has to make standing waves on the orbits, right? So the standing wave will require that the circumference of these orbits are integer times the wavelengths of the electrons, either 2 times or 3 times or 4 times. So this gives you the orbit number 2, orbit number 3, and orbit number 4, right? So this more or less explain the discrete orbits. So the Bohr model, if you add up on it the wave property of electrons, you can more or less explain the quantization of orbits, and this is what we call the old quantum theory. And you know that we call it old quantum theory because nowadays we don't use it anymore. We only use it in teaching, in doing public promotion. And actually later we realized that the true quantum theory are much, much richer than this. And here comes Schrödinger, right? So probably you learn from your chemistry class that electrons are actually not fixed into orbits. It's very naughty. It just goes here and there, and you cannot track the location. And then this is what we call the electron clouds, okay? So the Schrödinger and contemporary physicists realized that the electrons, they don't want to stay there. They're very naughty. They will not stay in a fixed orbit. And we human beings, we have to completely abandon this idea of fixed orbits. And when we talk about the location, we don't use the idea of orbits. We can only use the idea of probabilities, right? So if you ask a question, where is the electron right now? You are asking a forbidden question. You're not allowed to ask this question. There's no such question in the quantum mechanical world. Instead, you should ask the question this way. In this narrow space, in this narrow portion of the space, how likely I can find an electron? Whether you find an electron or not, I don't know. I cannot know. I can only know the probability. And then if you want to confirm the probability I give you, you should not only do one measurement. You have to do 100, 1,000 measurements, and you collect the probability. Everything you think real is made up by things like this, not real. You have to do it many, many times in order to reveal a probabilistic pattern. And we know that this is very hard to understand, and that's why I asked my friend Dr. He Mingquan to produce a VR set. Later on you can click measurement, and you can see that you are making many, many copies. There's a feature, right? You can make many, many copies. You can understand what measurement is really going on, right? So this explanation based on probability has actually profound consequences on science. Before that, nobody cares about probability. We think that this is real. This is here forever, right? I'm here, and then this color is like this. The electron is in a state forever. And now you said everything is based on something which is not real, which is based on probabilities, right? So it is the atomic model of the Schrödinger, which is what we use today. And since this is a popular science lecture, let me use the Schrödinger's cat, very famous. I'm pretty sure many of you already know it. Let me use the Schrödinger's cat to try to explain some of the interesting facts of quantum mechanics. So the Schrödinger's cat is a very interesting thought experiment. We will not poison a cat in real world, okay? It's a violation of law, but we just do it in our head. Imagine that we have a box, the box is closed. So once you put a cat in it and you close the cover, you will not see what is inside. Right, so there is a bottle. The bottle has a poison inside, and there's a hammer hanging above it, and there's a radioactive source, which is probabilistic. With 50% of the chance, the radioactive source will eject a particle. The particle will activate the hammer will break the bottle release the poison, and the cat will be dead. With the remaining probability, the radioactive source will do nothing, okay? And the hammer will not fall down, and the bottle will be intact, and the cat is safe, the cat is alive. And the question is that before you open the box to examine the state of the cat, what is the cat like? Of course, after you open the box, the cat is either alive or dead, right? But before you open the box, what is the state of the cat? And Schrödinger has thought about this many, many times for a long time. He has to conclude that the cat is in a combination of alive and cat, because these are all probabilities. These are all possibilities, right? So if I tell you, Professor Wang lives in this complex, which has building number 1 and building number 2. If I don't tell you which building I live in, you have to accept that there are two possibilities. I can either in building number 1 or building number 2. But if I tell you I am in a building where the number is a prime number, and you know I'm in building number 2, and the probability I'm in building number 1 just suddenly fall down to 0, and the probability that I'm in building number 2 suddenly increase to 100%. Right? This is the action of measurement or opening the box. Okay? So Schrödinger concluded that you have to accept this superposition of alive and dead. And there were a lot of artistic indication, right? So this cat is half alive, half dead. This is half alive, half dead. And then they combine this alive and dead in the same word. And this is what we call the Dirac notation, that we'll come back to this a little bit later, that this shows the superposition of the states, right? So as I said, I promised you, at some point, I will pause, I will stop, and ask you whether you are shocked. Are you shocked by Schrödinger's cat? So those who are shocked, please raise your hand. Not many, okay, thank you. If you're not shocked, it's not because you don't understand. It's because I don't teach well. Okay, so I apologize, I don't teach well. But there is a very good reason that I stop here. Why I stop here and ask you whether you are shocked or not? Does anyone know why I stop here? So this is called Schrödinger's cat. It's not just you being shocked. Schrödinger himself feels shocked. He feels so shocked. He feels this is so absurd. I'm not making it up. You checked history, right? So we learned a new English vocabulary here, absurd. He feels this is so absurd that he gave up physics completely. It was during the World War II, and he hid himself in Ireland, in Dublin, and he doing a few other lectures, and he became a biologist. He seen that, hey, I should do something other than physics, and then he chose biology. And then he later on published a book named What is Life? Okay, he made two very important contributions in this book. Number one, he realized that the biological, there's a biological inherence, there has to be a genetic code in the cell, which carried down from generation to generation, which later inspired Watson and Crick to discover the double helix nature of DNA. Another thing is that the life is based on the negative entropy. Right? If you ask your friend, why do you need to eat lunch? Why do you need to eat? What do you need from the food? Most likely they will say, I need the energy. It is Schrödinger who realized that it is not the energy that we need. It is the negative entropy. Right? In the future, if I have time, I really want to tell you this very exciting thing about the second thermodynamic law, the negative entropy. But today, due to the time limit, we continue our journey in the quantum world. So I want to tell you that Schrödinger feels that it is absurd that he gave up physics. But unfortunately, this is entirely correct. The Schrödinger's cat state has been constantly being produced in laboratories worldwide. This is very fundamental. Every quantum physicist, every experimentalist, they create Schrödinger cat state. Of course, not with a cat, right? With a cat is a macroscopic object. But with atoms, with electrons, with lights, and then you say, okay, they are all microscopic. Can you make it larger? Yes, we can do it with circuits. A circuit, we made it small, but not so small. Maybe 500 nanometer. It's already kind of very big. A circuit can have currents, clockwise, counterclockwise, representing alive and dead, and we can actually combine the two states together. And these are the paper. So Schrödinger was correct in proposing the Schrödinger's cat, and Schrödinger was wrong in saying that this is absurd. This is not absurd. So sometimes I always advise my students, sometimes after having a days of homework, you pause, you sit down and think, and look at this beautiful sky in Hong Kong and look at this beautiful Victoria Harbour, ask questions. Okay, so I want to ask this question. So Schrödinger made this mistake. Schrödinger, he was very brave. He was a pioneer. He go forward one step and he took a step back. Is he still great? The answer is he's still great. Right? Because he's still brave enough to break through, to move forward one step, even if he took back the step. Actually, this disease is not just him. Planck is the one who actually proposed the energy quanta, the first human being. But Planck also doesn't believe himself. Planck believed that this theory based on this discrete quanta is so ugly. The theory in God's hand that we human being doesn't know must be continuous. And we human being, we have to do this is just because we're not so intelligent. It is only a temporary solution to the problem with energy quanta. Planck doesn't believe in himself. Einstein wrote a paper on something called the hidden variable, but he retracted the paper. Einstein also made mistakes. All the human beings made mistakes. So young students, young fellows, don't worry, you are not perfect. Nobody is perfect. Schrödinger is not perfect. You only have to be brave enough to break one wall, to make one step further, further than your peers. And that's already good enough. Okay, and this is some lesson. So again, this is a popular science lecture, right? So this is a very famous parallel world explanation that the entire world, whatever happening is like a big movie. It's like a big drama that, all these events, whether the radioactive source produce a particle or not, will create a bifurcation, will produce branches, right? So in this case, if the radioactive source produce the particle, the cat will be dead, the cat enter this world. But there's another possibility that, the cat will be alive in the other world. You can imagine that every choice that you have made will lead you to one parallel world, right? You made a choice that you choose University of Hong Kong instead of CTU, or you choose to go to the United Kingdom instead of going to the United States. Every choice that you have made will lead you to one parallel world that you can only think about what would it be if I made another choice. You can only think about the other parallel world, but you are not able to turn it through. This is a parallel world explanation of quantum mechanics. So this is also a very famous experiment in statistics, in math. This is called the central limit theorem. So if you have a sufficient number of balls, and the balls are going down, and in every part, the ball has to make a decision, has to make a binary decision to left or right, and this is completely random. And the answer is that if this is completely random, and you have many balls falling down, it will make this pattern. This pattern is Gaussian, okay? So it is just like a world, like a society that everybody is making choices at different locations, and we arrive at different phases, right? So a very famous Taiwanese writer, she wrote a book, Jimmy, she wrote a comic called Turn Left, Turn Right, right? So the boy likes to turn left, the girl likes to turn right. They made this decision, so they never met. And of course, they met eventually, and they create stories. And I just want to produce this figure because I thought this is a very good explanation of making decisions. So by the way, there's a human-sized depiction of this comic, which is in Taiwan, right? So the reality is like a constantly making choices. You make a choice going to the left, to the right, going to this school or that school, right? You choose to come to this lecture or not, will all change the eventual fate of yourself. So now, let's try to understand quantum communication. So before you observe the cat, it is in a combination of alive and dead, right? After you observe the cat, it's either alive and dead. A combination of alive and dead and either alive or dead, these two are different, right? So I tell you, I live in either building number 1 or building number 2, right? And then you ask me, which building exactly, Professor Wang, you're living? I say, I live in building number 2. And then I live either in building number 1 or building number 2. But you will not be able to come back to the original state that I have 2 possibilities. Because once you make your measurement, there's only 1 possibility remaining, either this one or that one. So by measuring the state, the cat state or other state, it kind of collapses to one of the possibilities. Before you measure, it's a combination of possibilities. And after you measure, it's only one of the possibilities. It's just that you're not able to decide. You're not able to know a priori which possibility it is. So by making this action of doing observation, you change the state, okay? And this change is irreversible and permanent. Using this fact, we can do quantum communication. So this is the principle of doing secure communication, that you have information. We call it the public, right? So this is a public information, right? The information. And then you have the key. And you don't want to send this original information all over the world, because it's all sent by electromagnetic wave, and everyone with the right signal, with the right frequency can receive it, can catch it. And that's why you see in the TV show that during the war, and the different parties, they try to catch the other party's communication. It's very easy to catch all the signal that you have sent. So that's why when you send a signal, you have to mask it. You have to mask it with the keys. And mask with the key that I say, well, if they're the same, then write 0. If they're different, I write 1. So 0, 0, give me 0. 1, 1, give me 0. 1, 0, give me 1. And 0, give me 0. 0, 1, give me 1. So it is this masked information that is being sent all over the world, okay? And because it is masked, even if you catch it, you don't know my original message. You will only be able to know my original message if you have the key, right? So the safety of the key becomes so important. And that's why, I see that many TV shows, there are many movies produced by different companies saying that during the war, people have to use their life to protect the key. Or there are spies, they risk their own life, they take a picture of the key, and they try to send to their own parties. Right? That's why the key is so important. But it's so easy to lose the key, and that's why in modern cryptography, we don't use this method. We use something else called the RSA method. Right? So we use the fact that a big integer, it is very hard to factorize. So one eavesdropper will make the entire communication fail. And now we have quantum keys, right? If the key is transferred quantum mechanically, right? And then if Alice wants to send Bob the key, Alice sends out a red envelope, okay? And then if Eve have eavesdropped the key, if somebody has stolen the key, and then we know that he or she will change the state forever. Let's say it changed the envelope from red to green, and Bob received a green envelope. And now Bob doesn't even need a quantum channel. Bob just has to grab a regular telephone and call Alice. Hey, I received a green envelope. Is it what you sent? Alice said, no, I sent you a red one. It means that the key, the security of the key has been compromised. And then what we do, we just throw away the key and transfer the key again until we receive a safe key. And then I say, hey, my key is safe, your key is safe, only you and me, we have the key, and now let's start the transmission of the masked message. Okay, so this is the idea of quantum communication. So according to the principle, it is absolutely safe. And of course, you can discuss with me, well, there are a lot of loopholes. Someone can actually catch a key and copy the key and give it to you, and there may be loss in producing. All these are technical. So when I came to Hong Kong, and about a year later, Professor Pan Jianwei in mainland China, he shot up the world's first quantum communication satellite into the space. And that's why later on ignited a race between China and US. Now quantum technology become the battleground between countries. And you might now know that a lot of scientific equipment we can no longer buy, even Hong Kong. So to do quantum research, we need something called a dilute refrigerator. It's just like your fridge, but that fridge can go down to 0.001 Kelvin. Okay, very low temperature. Previously, we buy it from Finland, from something called Blue Force. But December 2022, we received the last shipment. And after January 2023, China, mainland, and Hong Kong, we can no longer buy. They return our money. And then, but of course, we have something produced domestically. It's not as good, but it's doable. And then now we can start doing research using domestically produced equipment. I tell you this story because I want to let you know that we are on the verge of the fourth industrial revolution, or the second quantum revolution, which use exactly this, exactly quantum measurement, quantum entanglement or so. And this field has already become the battlefield of countries. China, United States, European Union, Australia are the key players here, okay? So this is quantum communication. So I want to emphasize that only the key is being transferred quantum mechanically, and as long as you receive the key and verify the key, all other information can be transferred regularly with using the classical channel. So the quantum channel will not replace the classical channel. So 10 years from now, actually even now we have products called QKD, quantum key distribution. It's just that you may not need it. It is those who care about the security very much, like in the bank, like in the military, sometimes they buy this equipment. But let's say 10 years later, if somebody bring a QKD and they want to sell you, hey, you buy my QKD equipment, you can throw away your cell phone, and you say, hey, you're cheating. Because 10 years ago, in 2025, Professor Wang is telling me that only the key is being transferred quantum mechanically, and this cannot replace the classical method of doing communication, okay? So here comes this quantum entanglement, right? So we have a cat state. We do measurement. Outcome number one, it is alive. Outcome number two, it is dead, right? No problem, no problem. So now I make up these states. This is something called the Bell state. The Bell state says that the cat has to be simultaneously alive or dead. So initially, I prepare two cats, either both alive or both dead. We call it Bell state. And if I do measurement number one, outcome number one is both alive. Outcome number two is both dead. No problem, okay? So here comes the miracle. The miracle is like this. If now, today, in the Hong Kong Science Museum, I produce two cats, and then I make sure that they're in the Bell state, so they are entangled. But I put the two cats in two different boxes. The boxes are all, of course, closed. You're not able to see. So I take one box, and you take one box. And at this moment, our cats are both 50% alive and 50% dead. And now I take a light speed rocket. I bring my cat to this side of the universe. And you bring your cat to the other side of the universe. We are so far away that even light cannot communicate. Even light can take 100 years to communicate. So 100 years later, we reach the end of the universe. And then I made my measurement, okay? And you don't have to make measurement. I make my measurement, and even my cat is alive, and I'm sure that on your side, without making any measurement, your cat will be alive. If I make my measurement, my cat is dead, and you don't have to make another measurement. Your measurement will be useless. Your cat will definitely be dead. So the cat, the fate will be linked. And this link seems like going above the light speed, right? So this is what Einstein feels very, very strange. So once produced entangled, the fate of the two cats are entangled, are linked, even if they are on different sides of the universe. And this is what the discussion has done in 1927. And Einstein was so shocked. Einstein said, this is something called the spooky action in distance. Spooky is a word that I rarely sing, except in October, right? Disneyland has this spooky Halloween. But this is because all the human being, all the physics that you have is because we don't believe in action in the distance, right? You hit me, I feel painful because you hit me, right? If I do this, you feel painful, it must be something that from me which has hit you, right? If you hold a charge and I hold the charge, I repel you because my charge produces electric field. Or if I hold a magnet, you hold a magnet, you feel force because my magnet produces a magnetic field. And now you're telling me that I don't need all of this. There's a simultaneous action in the distance that even light cannot carry through. Okay, Einstein called this spooky action in the distance. And then we feel that the spooky action in the distance is too troublesome, too long. And we try to replace these four words by another word, entanglement. So entanglement means exactly this, spooky action at a distance. Once they are linked, they are just act like one. You measure one part, it's like you measure the other one simultaneously. And you don't have to make a measurement. It will change the state simultaneously without the light carrying the information going there. Okay? So this is something very strange, which will lead to discussions, I'm sure, in other places. People keep questioning me on this for 1 hour or so. I know this is very hard to accept, but we have experiments to show that this is true, and we have to accept this. Right, so this is the 2016 version that people have done this with 6.2 kilometers in Canada and 14.7 kilometers in Shanghai. And then actually, I just checked the literature. In the last year, in 2024, the longest distance we have done is 30 kilometers. So we bring the two states 30 kilometers apart, and we know that measurement on one side will instantaneously affect the other. Right. So this is called the quantum teleportation. So the last part, maybe I have a few minutes to talk about my research on quantum computation. So to understand quantum computation, we first have to understand classical computation, which use bit, right? 0 and 1 are bit, are the fundamental units for computation. And we have operations on the bit, which are called gates, right? So I really like this word because the gate, which has not, I'm 0. I walk through the gate, I become 1, right? Or I have hand in hand with another bit, I went through another gate called AND gate or another gate. So so 0, 0 becomes 0, 1, 1 becomes 1. It also turns out that if you know how to do a NOT gate and another 2-bit gate, this is actually XOR gate, you can do universal computation. So in all your computers, the entire thing of making a chip is to trying to make all these gates. It's just billions of gates. So it's much easier said than done, but it's easier being said, right? So I just said all the things that are being carved on the silicon is all these gates. So for quantum computer, we have quantum bits, and we take these cat states. Of course, I'm not a very good painter. It's a big job for me to keep drawing cats. So I would rather not to draw cats. Instead, I label this by 0. I label this by 1. I also know that the probability may not be half-half. In reality, may not happen to be. So that I have A, I have B. So congratulations, you have just written down a quantum state. And we usually represent the quantum state on a sphere. We call it the Bloch sphere, right? So this because two variables, right? So student, 2 variables will produce a surface. 3 variables will produce a body. So now we have 2 variables, and the variables are linked to each other. So this actually corresponds to 1 point on a spherical surface. So we call this Bloch sphere. And the 0 is just like a North Pole, and the 1 is just like a South Pole, and A0 plus B1 is just some point on this sphere. So you realize that for classical computation, we only have a 0 and 1, right? For quantum computation, any point on this sphere is meaningful, right? So in your drawer, instead of having 0 and 1, black and white, now you have the entire color set. Wouldn't it be amazing? Okay? Second, not only we can store an entire color set, we can have much, much more operations. So the classical computation is just like a world with only 2 cities, with only 2 airports, right? We have a NOT gate, right? Changing 0 to 1, 1 to 0, just like you can only fly from the North Pole to the South Pole, or from the South Pole to the North Pole. How boring the world will be. But now we have a block sphere, which we can change from any point to any other point on this sphere, right? This is called the single qubit rotation, right? We have much, much more operations. So the quantum computer is much more powerful because, and of course we are limited by the time, and I cannot give you much, much more details. But I can tell you that number one, it's much more powerful because we can store more in one register. We can operate, we have much more operation. And most importantly, but I don't have time to tell you, that it is the linear superposition and entanglement which allow us to manipulate many quantum bits at one time. This is called massive intrinsic parallelism. Okay. So in fact, the quantum computer can only do good things on selective problems. For example, searching big data. We have a very efficient searching algorithm called the Groover algorithm. And then we can also design drugs, design materials. You don't have to really make up the drugs. You don't have to really make the material and under test. We can test it using simulation. We can do machine learning. We can do cryptography. However, it cannot replace your classical computer, right? You still have to play video games or you watch YouTube on your classical computer. It is only on these selective problems that you have to run through a quantum computer 10 years from now, let's say. So these are the 2022 Nobel Prize in Physics. They have done experiments in entangled photons, which have proven the existence of entanglement. Right? So they have proven that this entanglement of the states is true. Right? So they are Aspey, Clauser, and Zeilinger. And Aspey actually is one of the senior fellow of CTU's Institute for Advanced Study, and he has came to CTU to deliver courses. Okay, this is actually Zeilinger. This is Aspey. Right? So in CTU, we have a big team of doing quantum information research that we welcome young friends to join us in the future. Right? So quantum computation, quantum technology is a very big field. There are mathematicians. They say, well, if you have a quantum computer, what good algorithm we can do? There are computer scientists. They care about what is computable, what is not computable, which one is equivalent to an algorithm on a Turing machine. But we, as physicists, we care more about how to realize a quantum computer. How can we make a quantum computer so that 10 years or 20 years from now, you can do your searching with a quantum computer? So we care about the physical candidates. So there are lights, right? Light can have different polarizations. You can have polarizations vertical. You can have horizontal polarizations. You can have 45 degrees polarization. You can have counterclockwise or clockwise polarizations. These are all used to quantum computation. You have atoms. Atom can have different kind of quantum states, right, which can do quantum computation. And in Hong Kong UST, there's a group doing atomic quantum computation. So circuits, I said that, right, so we can create catch states using circuits. So in CTU, Professor Yu Chun-Hui, so his group is working on superconducting circuit quantum computation. So ions, right? Ions is also like atoms, but ions are charged, right? So we can also use ions. We can also use lasers to trap ions, which can do quantum computation. But in Hong Kong, I'm not aware of research group. In mainland China and the United States, there are research groups working on using ions to do quantum computation. So electrons in semiconductor is actually my research. I do theories on these quantum dot electrons. And unfortunately, these experiments are so challenging that in the entire world, there are less than 10 groups which can do this experiment. There are this University of Tokyo, there are University of Science and Technology in Hefei, China, and there are groups in the Delft, Netherlands, there are groups in the Wisconsin, United States, and in Sydney, Australia. Not many groups can do it. These are really the forefront of the intelligence of human being. And then also electrons in diamonds, sometimes diamond has these impurities, and the impurity can carry electrons, and we can use that electron to do experiments. In Hong Kong UST, we have a group working on this. So it comes to the end of my lecture. You know, looking forward, we are still far away from the truth. We are far away from our goal. Nobody have a quantum computer yet. The quantum technology is still under government proposal. It's not in your life. It's not like ChatGPT, everybody's using it, right? We still have a long way to go. We still have a long way before we can make quantum technology to benefit every human being, everyone. But looking back 100 years ago or 500 years ago, you know, starting the age of Planck, starting the age of, for example, Einstein, we are already making a lot of progresses, right? We can create cascades. We have so many sophisticated equipments. We can manipulate, you know, 10 or 50 or even 100 ions. We can comment, you know, 100 atoms. We can actually make 100 atoms to make into patterns, to create words, and then we can make them to do computation for us, to do simulation for us. So we are already very far away from where we used to be. And this is a triumph of human being. And as physicists, we are proud of that. So we said that Einstein and Bohr, they had a lot of argument. They had a lot of discussion. This is one of the very famous quote. And Bohr said, for a parallel to the lesson of atomic theory is actually quantum mechanics. It's just that at that time, it was not the official name. We must turn to those kind of epistemological problems with which already thinkers like the Buddha and Lao Tzu have been confronted. When trying to harmonize our position as spectators and actors in the great drama of existence. So what this means, right? Epistemological meaning something superficial, something not down to the earth, something kind of philosophical, abstract, superficial, related to what you think. What problem? This problem has been thought by Buddha and Lao Tzu. What problem, right? So the entire world, entire reality, everything happening is a big drama, right? So I'm producing a drama. But in this big drama of existence, are you sitting way in the back as an audience, or are you actually one of the actors, right? So when you go to the Hong Kong Space Museum, they will tell you observable universe, right? So we have observable universe. So one of the Nobel Prize winner, Wheeler is the father of the hydrogen bomb. He said that observable universe may not be a good phrase. Why don't we say participatory universe, right? Observable means that you are sitting all the way in the back. You are observing it. But actually, according to quantum mechanics, everything you have made, every food panda you have ordered, every air ticket you have purchased, every decision you have made, they all come up together and forming this greater drama of existence. You know, when I was a child, when I was about P5, P6, I had insomnia, I couldn't sleep. I was thinking about, you know, this entire world, why it is real? Do I have proof it is real, right? Is it just something created by my dad, my daddy and mommy? They love me, right? When I want good food, they give me good food, right? When I take examination, I have good grade, and the teacher praise me. Everything seems so good. Is the world real? They produce the world, or the world is not real, right? I've been thinking about it. And maybe young friends, young students, when you go back home, you can think about this, right? In this, number one, in this greater drama of existence, are you an observer or are you one of the actors? And number two, is the reality there independent of your measurement, independent of your participation, or the reality is not there without your participation? So with that, I end with a quote from Stephen Hawking that science is not only a disciple of reason, but also one of romance and passion. So this lecture is a bit long, but I hope I have brought you the passion of physics. Thank you very much.